We will start now with the topic of curve sketching analysis, one of the central topics in differentiation. In this chapter, we're going to look at increasing and decreasing functions at stationary points and minima and maxima, which are special stationary points. We start with the definition, namely we're given a function f and an interval s that is a subregion of the domain of the function. So we have here the x-axis, and then on the x-axis somewhere we have our interval s. All the x values within this interval, that's meant by that. And now we say the function f is increasing in that interval for these x values. This means that if I take any two x values in here, x1 being to the right of x2, x1 being larger than x2, so here somewhere on the right, this on the left, then it's increasing. This means that f of x1 is larger or equal than f of x2. I mean, f of x1 drawn on the y-axis is larger or equal than f of x2, so we see it goes up here somehow. If this now holds for any two x1 and x2, if I take here x2 and here x1 or whatever I like, if everywhere I have this that it's going up, it means it is increasing on the whole interval s. The same way I can now define it is decreasing. Again, still x1 is to the right of x2. Now it's decreasing if the x1 is smaller or equal to f of x2. So I have, for example, here the x2, then the f of x1 has to be just smaller or equal. Then we add now the term strictly, so we get, we can say f is strictly increasing on the interval, then it has to be, the f of x1 has really to be larger than f of x2, it can't be the same. If it's strictly decreasing, it has to be smaller, it can't be equal. And a last important definition is we say f is monotone, increasing or decreasing, or monotone, strictly increasing, decreasing. If this applies on all of the domain, then we talk about monotone. So to understand better what I explained, let's look at this function here, and let's find now first where is f increasing. Have a look at the graph, think about it, and try to fill in the interval on which it is increasing. Do it on your own, and here comes the result. So the function is increasing all over here and all over here. Note here it is horizontal, but this means that it is just not decreasing, so we say that's okay. As long as it's not decreasing, we can call it increasing. If we say strictly increasing, then this is not allowed, it can't be horizontal. The point to the right has to be above the one to the left. For increasing, it's enough if it's just not below. So try now to find where is f strictly increasing. Stop the film, here comes the result. So strictly increasing, it is here strictly increasing, then here, and then here. Now find where it is decreasing. Stop the film, here comes the result. Well, probably you forgot about this region. Well, here, since it's horizontal, we can call it decreasing, or it's also decreasing here, and then it's again decreasing from here to here, and then from here until infinity. Where is it strictly decreasing? Here comes the result. So it is strictly decreasing here, and then from here all over. One question is this point here. Here it is not meant to be for longer time horizontal. This is more a point, a saddle point, as we know it from x to the power of 3. We'll discuss that in a moment. Where is f increasing and decreasing? Well, have a look at it. Here is the result. It is obviously in these two regions where the graph is horizontal. Now, what we are really interested in is to find the relation between the statement that f of x is strictly or non-strictly increasing or decreasing and f dash of x. So if we know that f is increasing on s, what can we say about f dash of x? Think about it. Well, we know that f dash of x is larger or equal to 0. All over here, it is increasing. It is strictly increasing on the, sorry, now, when do we know that f is strictly increasing on S? We know that's then the case if the f dash is positive. So not larger equal, but larger. Note, here we have the implication from the left to the right. Here actually the implication is from the right to the left. That's a little bit tricky, but for the moment not so important. When is f decreasing? And when it is, and the opposite way, what do we have to know about f dash? That we know it is strictly decreasing. Think about it. Complete the film, the script, and yes, it is. If f is decreasing, then f dash is larger equal to 0, smaller equal to 0, obviously, and if f dash is smaller than 0, then we know that f is strictly decreasing. Let's look now at the special example f of x being x to the power of 3. You remember f of x being x to the power of 3. It looks somehow like this here. And we have this point, this saddle point at 0, 0. Now, x to the power of 3 is strictly increasing on all of R. Why is that the case? I mean, we might discuss, is it really strictly increasing here? Well, when at x being 0, it looks like it's horizontal, but when we go just a little bit to the right for x a little bit larger than 0, immediately we get a positive value, which means when we go from 0 to the right, it increases. When we go from 0 to the left, x to the power of 3, we'll get something negative. So it is all the time, when looking from the left to the right, it is all the time increasing. So, but at the same time, f dash of x, f of x being x to the power of 3, f dash of x is 3x squared. So f dash of 0 is 0. So this is the explanation why we have a little bit these tricky things with these implications from right and left. That's exactly about these situations. For all the rest, it's unproblematic. Definition: a stationary point of a function f is a point where the derivative is 0. This means it's a point where the tangent to f is horizontal. Stationary points are points where the tangent is horizontal. And there are 3 types of stationary points, namely extrema. They are also called turning points, local maxima and local minima, which are shown here. Here we have a local maximum. Here is the highest point. A local minimum is here. And stationary inflection points are that what we called so far saddle points. These are called often just stationary inflection points. And what is important for local maximum, minimum, what does it mean? When do we talk about the local maximum? It means that in very close to this x value here, the y value of this here at this point is the largest one. So if I have something like this here, this is nevertheless a maximum because very close here, it is the highest point. The opposite way, it's the same for a minimum. So now let's find stationary points. Let's find all stationary points of this function f, and then we want to sketch a sign diagram of f dash and the graph of f. In order to find all the stationary points, how do we proceed? Well, we have to find all points where the tangent is horizontal, which means the f dash of x has to be 0. So we have to start by finding f dash of x. So do that on your own. And here comes the result. So this is f dash of x, and now we said we're looking for all the points where the gradient is 0, the tangent is horizontal. This means where the f dash of x is equal to 0. So solve this equation, find the x's and the corresponding y. so that we can sketch the graph a little bit better. So here comes the result. We have stationary points at x equals -3 and x equals 1. Now let's sketch the sign diagram of f dash. This means we need the Zahlenstrahl, don't remember at the moment. Then we have x and f dash of x, and we note now all the points where f dash of x is either not defined or where it is 0. Well, f dash of x is obviously everywhere defined, x squared plus 2x minus 3. So where is it 0? It's 0 at x being -3, and it's 0 at x being 1. Now let's find for these three regions whether the f dash of x is there positive or negative. To the left of -3 we can insert -10. -10 we get 100. -20, -3, well, that's obviously positive. Then between -3 and 1, let's take a point. The simplest one is 0. Insert it here, 0, 0, we get -3 is negative. And last, to the right of 1, we can use 10 again. Well, 10, 100 plus 20 minus 3 is obviously positive. So this is the sign diagram telling us that the f dash of x is positive to the left of -3, which means the graph is increasing. It is negative between -3 and 1, it's decreasing there. And to the right of 1, it is increasing again. So let us sketch now the graph of f. Something like this here. So at x1 equals -3, we have to go up to 9. That's somewhere up here. Then at x1 equals 1, we go down to -5/3. And now what we said is the graph is increasing here. So it looks something like this. Then it is decreasing down to here and increasing again. So that's the way we get our sketch. That's it. Okay, here I provide an exact definition of a local maximum and minimum with a translation in a little bit more understanding terms. Here this being very mathematically formulated. This is still quite mathematical, just for those interested. Let us look at one last thing. That's namely how to find and classify stationary points of a function f based on f dash, and that's something we're going to do on and on. So it makes sense to look at that closely. So the first step, find the derivative and set it equal to 0, and in that way we find the x values of all stationary points. And then the question is, how can we classify these points, so as a maximum, a minimum, or as a stationary inflection point? So let us assume we have a local minimum. A local minimum looks something like this here. So at x0 I have a local minimum. So let us draw the sign diagram of f dash. This being f, here now the sign diagram of f dash. Go ahead, complete it. Here comes the result. Obviously it's negative here and positive here, and here it's 0. So what do we see now? F dash switches, when it's local minimum, f dash switches from minus to plus at x0, at x being x0. Now try the same thing for the local maximum. Do the complete thing, and here comes the result. We have the local maximum, so at x0 f dash is 0, horizontal tangent. Here f is increasing, the tangent has a positive gradient, so f dash is positive. Here to the right the tangent has a negative gradient, f dash is negative. So when we have a local maximum, what happens is that at x equals x0 the f dash switches from positive to negative. Last, let us look at a stationary inflection point. Well, for stationary inflection points we have to distinguish two cases. This is a stationary inflection point, or the second type of an stationary inflection point is obviously this here. So I have A and B, two types. So find now the sign diagrams for A and for B. Here comes the solution. In the first case, A, f dash is all the time positive because everywhere the tangent is increasing, the gradient is positive. In the second case, it's the contrary. Everywhere the tangent is decreasing, its gradient is negative. So we get here 0 plus plus, and here 0 and minus. So we found when do we have a stationary inflection point, f dash does not switch sign at x equals x0. And that's it.